All right, guys. So I want to talk about you starting in Unit 2 here. We're going to talk about radiation in space. And radiation really does give us a lot of information about what we understand in space, mainly because we can't go to a lot of these far distances, but we can measure what's there in the radiation forms. And it tells us a lot. All right, so some of the things we're going to talk about in this unit. We're going to talk about part 1. That, of course, is information in the skies. We can't travel that far, so how do we measure that? What does it tell us? And how we can study like mainly light waves, which are made of photons, and what that information really tells us. Because if you go out at night and you look up in the dark sky, you do see those pinpoints of light. Well, those come out with mostly stars, and they generate cosmic rays and neutrinos, and we can collect these things and really start to take a look at them. And if you think about a telescope is nothing more than a big bucket for photons. So we're catching photons, and that's what we're really looking at when we look at telescopes. Part 2, nature of a wave and radiations and how we are able to use these different types of radiation. And then part 3 is the electromagnetic spectrum, which is far more than just visible light when we think about waves. It gives visible light, radio, UV, and IR. So we use all of these, and X-ray even, in many cases in space. Some of the interactions with radiation and matter. Take a look at that and the reflection and refraction. So reflection being in a mirror, refraction, light bending or bouncing off, say in a prism. Transmission, which many stars do, they transmit light. The scattering, absorption, and emission. We'll talk about thermal radiation, which is the measurement in temperature. Primarily we use Kelvin in astronomy, mostly because it's easier to measure, because it has a bigger scale and things are so incredibly hot or cold. So we use that. Some of the radiation laws we'll look at is Planck's equation, Wien's law, and the Stefan-Bosolman law. You may have seen these in chemistry or even physics. So we'll check that out. And then, of course, the Doppler effect, which is if you ever stand by a train and a train goes by with its whistle, it sounds loud and you feel it fade away. That's the Doppler effect. All right, so what does the information in the sky tell us? Well, we use electromagnetic radiation to tell us a lot of this. It's a transmission of energy from whatever the source may be. Maybe a star, maybe a galaxy. The best example of this, of course, is light, because if you go out at night, you look up, you see that light. That's the biggest one we use. The closest, this is a picture of the closest galaxy to us, which is Andromeda. It looks like a little smudgy light. It's almost 2.2 million light years away, so it's really far out there. We know it as M31 in astronomy. But you'll take a look at the different light waves and different types of waves. This galaxy generates all of that. And that's why we know so much, or we're able to gather a lot about galaxies and study Andromeda. It's very difficult to study our own because we're right in it. But Andromeda, we can see, we can measure these things in light. Okay, some of the refraction, reflection, like I talked about earlier. When your light turns on in your house, you can get a reflection off of a mirror, or even in the form of color off of other items to your eye, where you can pick that up. The sun, of course, emits light, which will come through. We get reflections off of light. The ground, the snow, glass transmits light, so it actually magnifies it some. And then, of course, the cones and rods in our eye help absorb light so we can see things. Shirt and colors, these things all absorb or deflect light, so we're able to see those things. All right, I want you to copy this down, which is the formation of a wave. Of course, whenever we talk about waves, this up and down, we're familiar with this. Light travels in this, and almost anything in the EM spectrum does. So when we talk about the wavelength of a wave, it's from peak to peak, or we can make it from trough to trough. But we never do just a half wave. We want to try and measure that whole wave. We talk about the amplitude. It's how tall it is. A lot of people have amps in their cars to make the sound go up more. That's why they use this. Okay, and then of course the trough. So we have a peak, or the crest, and the trough. And then the undisturbed state, which is the middle line. And that is not on there, but you really should call this the middle line. You grab my pen and make sure you have that. So we'll call this our midline. Okay, and that's this center line right here in the middle, or the undisturbed state is what this says. Okay, remember we measure waves from crest to crest or trough to trough. Okay. All right, an example of a mechanical wave that we see is if you throw something in the water, it has the ripples that come off. This is the same thing. It's the same wave. And wave is nothing more than a transmission of energy. So when a wave does this in a water, it emits energy and travels through. So it's the very same thing. It's just a very good visual example of what a wave is. And that's what we're measuring out in space. All right, so we also have to talk about frequency. A frequency is the number of crests that pass by at a certain point and a number per second. So how many are going to go by per second? And then a period is the time between the passage of the successive crests. So you remember that we had these lines that waved up. Okay, and the period of time is where the amount of time that passes. The period is from here to here. There you go. This is a period right here in between these. So if we ask for the period, that's what it is. Okay, and the frequency is how many of these waves, lambda, the sign for wavelength, like you see right here, lambda. Okay, is this wavelength? So that's the frequency. How many of these go by in a second from a given point? Okay, and you see the relationship is 1 through the period of time. Of course, if we know the wavelength, match it by the velocity, we can come up with the speed of light. Okay. All right, wavelength considers the distance between successive crests, and then the velocity is how fast they're and how quickly they're moving by. So there we are with wavelength by velocity, okay, and we get the wavelength. All right, and we're primarily talking about, right now at this point, we're talking about the visible light, which is primarily what we're focused on right here. Whenever we talk to the spectrum, we send a light through a prism, we can see the rainbow, and you probably know it as Roy G. Biv. Okay, you may have learned that in art, which would be red, orange, yellow, green, blue, indigo, which is not on this chart. Indigo would go right here, and violet. So Roy G. Biv. It's a good way to remember the visible light spectrum. And you can see that it measures from about 4.3 times 10 to the 14th, or 700 nanometers, to 400 nanometers. This is important to keep in mind when we talk about wavelengths, okay, in between this, for visible light only. We may even talk about radio waves, infrared, ultraviolet, X-ray, and gamma ray, all in space to help us build our picture. Hubble is really good. Hubble telescope is very good at helping us with this. All right, so that's the end of part 1. Real basic stuff, talking about just visible light, giving you an idea about what it is and why we measure it in space. The next part we'll talk about it a little more in detail. All right, talk to you later. Make sure you take your notes on this and write your summary.